Okay, so I think let's start. Welcome to the afternoon session with Chairperson, yes, Professor Masaki Usakawa and David Choi.
Okay, so welcome back to the session. So as a first topic this afternoon, Okubo-san will continue his lecture on text network.
Okay, thank you very much. So let me continue our discussion on the data network. So I will begin from this the definition of the data network page, and here we discuss briefly about the one-dimensional data network that the matrix elastic and when this was but so then in the next part I will discuss about the generalization of this matrix product state to the higher dimensional systems that is okay. So as I explained in the first part, there is an ADNO in the case of the quantum physics. So we can use this information to perform the data compression to represent our quantum state. That is the data network decomposition. This is again the structure view. So we only need to consider some subspace within the whole vector space because the whole vector, random vector picking up from the whole vector space satisfy the volume law, but our interactive state is satisfying only the area. So small items, and we can use such information to perform the data compression. I'd like to emphasize that today we only discuss about the quantum method physics, but same idea holds for any test. So we can find any application of this idea. Okay, so this is the schematic view of the tensor network. So we can consider the tensor network state or tensor network decomposition is just a generalization of the Lorentz approximation of the matrices. So by using the singular decomposition, we perform the Lorentz approximation by neglecting the smaller singular. And we generalize this kind of idea to general tensor like this. So this approximation means that we pick up the important correlation among the, for example, two parts, and one side and the other side in the matrix. So similarly, we picked up the important correlation by using the information of the quantum entanglement. And we can design some kind of the tensor network just characterize the quantum correlations. So this network structure characterizes the quantum correlation of our quantum. And typically, if we are interested in the three-dimensional quantum system, these types of the tensor network works well, as I will discuss later. Suppose our state can be efficiently represented by this tensor product state, then we can say that this is the huge data compression because the original tensor has the 2 to the n independent elements to represent this tensor. But if we can represent our quantum state by using this tensor network formula, then the number of independent elements is just proportional to the n, not the exponential of the n, because we have only the n tensor to represent the n of the n space system. So if this state, this tensor network state is a good approximation to our quantum system, the tensor network approximation can be used in the simulation of the quantum classical computer. However, the point is the network structure. Here we assume that the size of the tensor is independent of the system size n. So here D is the dimension of each x. So here we assume that the D is independent of n. However, such property is only for this tensor network structure correctly capture the entanglement structure of our quantum system. So that's the point. I will explain this point. Okay. Then first, I'd like to introduce you again the matrix product state that will correspond to the variation of ansatz for the DMRG. So in this case, we decompose our tensor into the chain of the small tensors like this. Okay. So that is as in the lecture yesterday, this corresponds to somehow the DMRG. Then here is one notice. So this matrix product state is also called as tensor train decomposition in mathematics, applied mathematics. So it is proposed in this paper. So if you want to apply the tensor network decomposition to the data science, you may find this name in the science paper. And also, there are another important information is that we can consider this matrix product state is a generalization of the product state. In the case of the product state, we represent our state as the product of local state like this. And so it corresponds to the case with the image, the matrix product state with the 1 by 1 matrix. So if the dimension of these horizontal legs equal to 1, then this matrix product state represents the product state. So if we increase the dimension in this horizontal line equal the order dimension in the tensor network language, then we can increase the representation power, representative power of our tensor state, matrix product state. Okay, then first I'd like to mention that any quantum state can be transformed into the matrix product state without any approximation. Okay, that can be done by using simple singular value decomposition, for example. So suppose we have the 5-leg tensor like this. This is the quantum state. Then we transform this tensor into the matrix with 1 leg by combining right 4 legs as the 1 index. So we consider this 5-leg tensor as the matrix with 1 row and 4 column consists of the 4 legs. Then we can apply the singular value decomposition like this by diagram. Then we call this unitary matrix U as isometry as A. Then similarly, by combining this lambda and B and construct the matrix B, tensor B, and then we construct, in this representation, B is 3. Anyway, by combining this lambda and B and by constructing the matrix like this and by applying the singular value decomposition, we again obtain this SPD formula, and now we call this U2 as a A2. By repeating this procedure, we finally obtain this kind of expression. It is nothing but a matrix product state. Okay. So here we didn't perform any approximation. So any quantum state can be transformed into the form of the matrix product state. However, in this matrix product state, the dimension of horizontal legs increase as we increase the system size. That corresponds to the increase of the dimension of the Hilbert space. For example, in the case of this 5-leg system, the first matrix is 2 by 16. So we have at most 2 singular values because the rank of the matrix is 2. Then the horizontal dimension is 2. In the second part, we consider the 2 by 8 matrix in this example. So the rank is at most 4. So the horizontal dimension here becomes 4. By repeating this procedure, the dimension increases as 2, 4, 8, 16, 32, blah, blah, blah. So if you increase the system size, at the center of your system, the maximum bond dimension is exponentially large. So this is because we didn't perform any approximation. However, if our quantum state has low entanglement, we can approximate this matrix product state by neglecting the small singular values. Singular values appears at this procedure. So if some singular values are small, we can safely neglect such component. So it means that the difference between the original tensor and the approximate tensor becomes smaller if the singular values are very small. Neglected singular values are very small. So in some cases, we can consider that we keep the maximum bond dimension. Maximum dimension in the horizontal indices are finite. Then in this case, we approximate our quantum state with only linear in the system size. If we fix the maximum size of our tensor. So we can say that if the entanglement entropy of the system is order 1, independent of the system type n, the matrix size chi can be small for accurate approximation. And because of this, the matrix product state is good for the gap one system as we discussed, because the entanglement entropy of the area in this case. On the other hand, if the entanglement entropy increases as we increase the system size, we need to increase its chi as we increase the system size. And so we cannot use the matrix product state to approximate our quantum state, which don't satisfy the one-dimensional area. So we can understand this property by this diagram. So suppose we have the quantum state, and it is represented by the matrix product state with the bond dimension I. Then let's calculate the outstate entanglement. First, we divide the system into two parts like this. Then we calculate we construct the reduced density matrix by tracing out the degree of freedom in region B. That corresponds to this diagram. It's okay. So by connecting these two lines between this trace operation. Anyway, this is the matrix. For example, upper part corresponds to the row, and the bottom three legs corresponds to the part. Then let's see the structure of this resistance matrix. The point is that the horizontal bond connecting between the A and B is high. So this matrix has this structure. So the two matrices are connected by chi by chi. It means that the rank of this matrix, resistance matrix, is utmost chi. Okay. So from this fact, we can say that the entanglement entropy calculated from the resistance matrix is bounded by log chi. So this is it is achieved by the Prof spectrum of the Schmidt coefficient up to from index 1 to 5. So the rank is the rank. But because our rank is high, we have at most finite, finite Schmidt coefficient, and so it gives us the upper bound.
Excuse me.
Okay.
So what did you use to derive the inequality?
What? So this one or
No, the last one.
last one. So you can find some fruit in some, for example, Wikipedia, in the difference. But the point is that if you accept that the maximum value of the entanglement entropy is given by the flat histogram Schmidt coefficient, it is trivial because the rank is equal to chi, utmost chi. Then actually the entanglement maximum value of the entanglement entropy is equal to chi because it is achieved if we distribute this high degree of So the whole symmetry coefficient is equal to
Or
1
like
over
distribution.
Yeah, it's okay.
Like distribution.
So I have a question. So now the situation you are dealing with is that you are approximating the wave function as the side tutor
Okay. So
with the
sorry, here I don't discuss the approximation. So suppose we have a quantum state represented by matrix products. Then I showed that you that if the bond dimension is at most high, then the entanglement entropy is bounded by log high. This quantum state has at most the entanglement entropy log high.
Okay.
So from this fact, so from this calculation, we didn't assume the length of the matrix product state. So it means that the bound of the entanglement entropy is independent of the length. Okay. So if we fix the bond dimension high, and if we increase the system size, we obtain the area law corresponding to the one-dimensional system. So it is entanglement entropy is independent of the system size. Okay. On the other hand, if our target state has size dependence in the entanglement entropy, then this already indicates that we need to increase high as we increase the system size to satisfy the scaling of the entanglement entropy. For example, entanglement entropy is log of n. We need to increase the high as this power law. And if the entanglement entropy increase as like this, or like higher dependent on area law, then we need to increase both dimension high in this exponential form. Okay. So this is related to why the matrix product state works well only for the one-dimensional system, and it don't work well in the case of the higher dimensional system. Okay. Okay. So because our matrix product state satisfy the scaling of the entanglement entropy in one-dimensional system, naively we can say that we can write the wave function of the translationally invariant infinite chain by repeating the same tensor as like this. Even if keep the size of the matrix, that this very large system satisfies the one-dimensional area. So it means that it can represent the one-dimensional physical state. Okay, even if we consider very long system. Then, okay. So similarly, if the entanglement entropy of the certain states satisfies the area law, one-dimensional area law, we efficiently approximate the infinite system with a finite size matrix T. So the point is that even if we fix this time, the scaling of the entanglement entropy satisfies the area law for the one-dimensional system. So we can use the finite size tensor to represent the infinite size compact state. Okay, then I'd like to discuss what happens if we apply this matrix product state decomposition for higher dimensional system. And suppose we try to simulate transverse with the Ising model in the two-dimensional system, Lx times Ly like this. Then the area law of this system indicates that the entanglement entropy is proportional to this L. Okay, for almost every page, every parameter, all parameters. Then, when we apply the matrix product space representation for the square lattice system, we need to map our matrix product space chain to two-dimensional system. Now, suppose we use the so-called snake-like form to apply the matrix product state representation for this square lattice system. Then let's calculate the entanglement entropy for this setup. First, we consider division of we consider to this partition. So the upper half is called A and bottom half is B. And second one is we divide the system into rectangle. So we can see the difference between the case 1 and case 2. In the case 1, we have many legs between the A and B, but in the case 2, we have only one leg between them. It gives us the difference. Actually, we by the same argument in the previous calculation of the entanglement entropy, we can say that if we calculate the rank of this setup, rank of the reduced space matrix in this setup, the rank is at most high to the LX, because we have the high degree of freedom in vertical legs. So we have LX legs. So the dimension of this B part matrix that corresponds to the previous this one. Here, this part coming from this B, connecting from connection between the A and B, and it is go to the height to the LX, and so it means that entanglement entropy is bounded by the LX not high. But if we consider entanglement entropy in this setup, we only have one leg between the A prime and B prime. And so in this setup, the bound of the entanglement entropy is only of high. There is no side dimension. Okay, so it means that if we assign a matrix product state like this, we can cover the quantum entanglement between the upper half and bottom half correctly, because it satisfies the area of the two-dimensional system due to this refactor elements. But if we consider entanglement entropy between the left-hand side and right-hand side, because we have only one leg here, it don't satisfy the area of for the constant height. Then it means that if you increase in the setup Ly, we need to increase to cover the two-dimensional area. So we need to have the Ly here, because this is a two-dimensional system. So it means that this matrix product state assignment works only for the quasi one-dimensional system, where this Ly is constant, keep constant, and we can increase Lx free for the fixed height. And this is why the so-called two-dimensional DFIG works well for this kind of cylinder or solid.
I have a question here.
Okay.
You have not connected the X direction, right? I mean, if you connect the lower portion, your structure to connect in around the X direction, and even if you cut the blue and this red, this thing, then you are cutting many bonds.
Yes.
So then your entanglement is going to be similar.
Okay.
Situation like first one.
In that case, the state is not the matrix product state. And actually, that is the generalization of the matrix product state to the higher dimension. So you consider, for example, square root of the test. Yeah, okay. I will discuss this in the next slide, maybe. Okay. So the point is that if we map the two-dimensional quantum system like this MPS, or if we approximate this two-dimensional quantum system by MPS, it cannot cover the two-dimensional area law. So in order to keep the, for example, accuracy of the approximation, we need to increase the size of local matrices, and so it means that we cannot switch, especially exponentially. So we cannot treat the not so large two-dimensional system in this setup. However, if we can design the correct tensor network, it can cover the two-dimensional area alone. We can approximate our quantum state efficiently within the tensor network population. And actually, that is the tensor product state. Okay, so this is again. So for higher dimensional system, we have the system size dependence in the entangled entropy. So we want to design the tensor network which satisfies this area. It can satisfy the area by keeping the size of the tensor constant as we increase the system size. Okay, and the answer is so-called the tensor product state or PEX, and that is like this. So the tensor product state or PEX has this kind of the tensor network structure. So suppose here we consider square lattice geometry. Then in the case of the matrix product state, we treat the 3-leg tensor, but here we consider 5-leg tensor. Like this. So that each tensor corresponds to the position of the spin, for example. And we call the dimension of these 4 vertical x as D, and it is called again for the dimension. So similar to the case of MPS, matrix product state, by increase this D, we can increase the representation power of our tensor product state if we consider variation. And then we can say that if we can treat the D to the infinity, it becomes in some sense. If we use this tensor product state as a variation answer. Okay. Then the point is that as we will see that this tensor product state satisfies the area of the entangled entropy. And so it indicates that as in the case of the matrix product state, we can calculate the infinite size system by using this tensor network. I will explain. So the first, let's count the bound of the entanglement entropy again. So suppose we have the square lattice system, then we consider this partition. So as the center part, we call this region as A, and the other part is B. Okay, then following to the previous calculation, our task is to count the number of legs connecting the region A and the region B. So in this case, we can easily see that we have 4 L legs. So the rank of the reduced density matrix of this region A is at most D to the 4L. There is the information. So D to the 4L in this setup. And similarly, we can consider the general hypercubic, dimensional hypercubic. And in that case, we can say that the number of legs correspond to the L, proportional to the L to the D minus 1. The case of the hypercubic lattice. And following to the previous discussion, we can say that the entanglement entropy is at most like this. So we have the L to the D minus 1 factor here in this setup. Okay. So this inequality means that at least the tensor product state can represent the area of the entanglement entropy for general dimension.
So when you split tensor into small tensors, is there any other parts going on other than SVD?
Okay. So it's probably a very good question. In the case of the matrix product state, we have the some deterministic procedure to decompose our quantum state in the matrix product state formula. But in the case of this text, it is not so easy to perform this kind of to construct this tensor network structure from the original vector. This is because, as we mentioned, we cannot use the simple singular value decomposition. We cannot use the singular value decomposition. It gives us the sum, or only give us the matrix. But here we want to construct a tensor. So Yeah. So there is no, I would say, general technique to transform the given quantum state into the discrete tensor product state. So it is very difficult task. So we need to somehow perform the iterative optimization by assuming the tensor network structure. Very much for your question. Okay. Okay, then so then as in the case of the previous matrix product state, if our state has the translational invariance, we can represent the infinite size quantum system in, for example, 2 dimensions by assuming the kind of the unit cell structure in the infinite size system corresponding to this translational invariance. For example, we can assume that this kind of 2-side unit cell and we repeat this red and blue inserts infinitely, we represent this quantum state satisfying this unit cell. We can also design another unit cell structure. And the point is that a lot of interesting problems in the quantum spin system satisfy such translational symmetry. So it means that we can use this infinite tensor product state to investigate the, for example, quantum frustrated spin system by using this tensor product state as the ansatz for the variational calculation. And in the following, I'd like to discuss about how to use this tensor product state for the variational actual calculation. But before explaining the technical details, I'd like to mention you the difference between the matrix product state and tensor product state. In the point of view of the computation cost, there is a huge difference. In the case of the matrix product state, we can contract our tensor network with constant cost, or sorry, not constant, polynomial cost with respect to the system size. So, for example, suppose we want to calculate the inner product of 2 quantum states, and the corresponding diagram like this. Then to contract this tensor network diagram, for example, we can calculate the matrix product from the left-hand side to the right-hand side. And there appear only the n matrix product. So it means that the contraction cost of this tensor network is order n, polynomial cost. However, if we want to perform the similar calculation for this square lattice network, like this, so probably we should neglect this black thick line. So here, please consider that we don't have any open x. And in this case, we can say that the contraction cost is exponentially large like this. So even if we represent our quantum state in the tensor product state form, in order to contract, this type of contraction is necessary for example to calculate the expectation value. So we need to calculate the expectation value by using this tensor quantum state. Then to calculate the contraction, we need the exponentially large cost. So it is impossible to perform the exact contraction, even if we obtain the very good quantum state representation. However, fortunately, in the case of the tensor product state, we have the good approximated contraction technique. And in practice, we can perform this calculation with very good accuracy. Then we can perform the practical calculation by using this tensor product. Okay, that is the introduction of the tensor product state. And in the next part, I'd like to discuss about how to contract our quantum tensor product state, and also the tensor product state can represent a lot of interesting quantum state, and also probably I have enough time. I'd like to discuss about how to optimize our tensor product state and also how to apply this kind of idea to the finite temperature state. So far, we only consider pure state, but we generalize this kind of the idea to the finite temperature simulation, which means that we try to approximate the density matrix instead of the pure state. Okay. So far, do you have any questions? Okay. Then, so as I mentioned, it is impossible to perform the exact construction, the higher dimensional tensor network, but there are several methods to perform the approximate construction of the tensor network. There are many techniques developed for the different fields. For example, we can use the real space renormalization group to evaluate the construction, or we can use the kind of the DMRD technique to construct this tensor network, or we use the different kind of the matrix product state that we call the Conan transfer matrix method, and the other method also. In these days, the most fundamental or most popular technique is this Conan transfer matrix method, and so I want to show you what it is, but I don't explain the technical details. So if you can see my GitHub repository, I uploaded this slide, and you can find the appendices at the bottom of this slide. And here and there, I show you some technical details to perform this Conan transfer matrix. Anyway, the idea is something like that. Suppose we have the two-dimensional tensor network, and here we want to calculate the inner product of two quantum states. Then the tensor network diagram is represented by this tensor network. So here we don't have the open leg because we consider the inner product. Okay. Then the point is that here we consider infinitely large system. Then we approximate such infinitely large environment by using this tensor network structure. This square matrix is called the Conan transfer matrix, and we use the additional H tensors like this. And here we introduce the additional control parameter chi, which determines the size of this Conan transfer matrix, and which determines the accuracy of this approximation. And the point is that we can efficiently optimize this Conan transfer matrices by using the original tensor network with polynomial cost of this chi and the bond dimension of the original tensor product state. And in total, the total cost is something like that. And anyway, the exponent is so large, but we can contract our tensor network. It means that we can calculate the expectation value with by avoiding the exponential increase of the computation. Here we consider infinite size system, and so if we hit the exponentially large computation cost, it is impossible to evaluate this inner product. But by using this technique, we evaluate the inner product of the infinitely large quantum system by some finite.
So why there is two? I mean, x e to the power 6 and e to the power 4.
Why?
Why is it different? I mean,
Okay. So there are several stages to optimize the tensor, and depend on the steps we have these two stages, and both of them can give us the larger contribution, leading contribution to the computation cost. So here I show you the two different scaling. But anyway, we need both of these costs. In practice, usually we scale this chi as d squared, and by substituting d squared to this here chi, and we obtain the scaling as d to the 10th. This is a typical computation cost for the tensor product state calculation. If you use the different techniques like the single layer approach or maybe the infinite environment, we can reduce this exponent, but typically it is d to the 10th. So it is polynomial of d, but it is still large. So that it is restrict the applicable d. Typically we can use only 20 or something like that at most.
So here, what is this entropy?
Entropy. Yeah. So basically the entropy is bounded by this one. So in the case of two-dimensional system, we have OL log d. But the point is that as we increase the system size, the entropy also increases. So it is not so easy to discuss the entropy of our infinite size system.
But still we have the same, I mean, increasing with the system size because it's a 2D into L log D, right? For
Yes.
2D. So, and how about the like a simple NPS stack?
Okay, so in the case of tensor product state, we have L to the d minus 1. It covers the area of the entanglement. And so it means that if we have the constant d is independent of the system size, we can represent the area of the entanglement. It is the crucial difference between the tensor product state and the matrix product state. In the case of the matrix product state, as I explained, so for this setup, we can represent the entanglement, the entropy, not proportional to the length of partial width. So matrix product state cannot represent the scaling of entanglement, scaling entanglement entropy in 2D if we fix this combination. But in the case of the tensor product state, even if we fix D, the scaling of the entanglement entropy covered by this tensor network structure. That's the point.
And is the length still?
System length or the system length of subregion. So here we consider the infinite size system. But the area of the entanglement entropy says that if we divide the system into two parts, then the entanglement entropy is proportional to the area between the region A. And we can discuss the entanglement entropy for the infinite size system. Okay, so now we can use this tensor product state to simulate our two-dimensional system by using this contour matrix environment. And I will skip this part because this is the technical details. But by using this contour matrix environment, we can easily calculate this expectation value by this diagram. So this is because this is finite, we can easily calculate this contraction, or we can also calculate the two sides expectation value like this, or we can also calculate the some kind of the correlation function by using this contour matrix environment. The point is that here we assume that the translation invariance. So it means that by repeating this H tensor, we can represent the very large cluster. So it means that we can use this environment to calculate the correlation function. And then also we can use this part as the transfer matrix for the correlation function. And by evaluating the eigenvalue spectrum of this transfer matrix, we can also evaluate, for example, correlation x corresponding to the some correlation function. Okay, that is maybe the standard technique for the data analysis of the contour state. Okay. Anyway, we can use this contour matrix environment to calculate several important physical. Okay, So now, once we have the tensor product state, we can calculate the expectation value. But the point, problem is that actually the tensor product state can represent the interesting quantum state. But then here I show you some example where the tensor product state can represent the quantum state. Okay, so this is the same table as before. So as I will discuss, for higher dimensional system, the leading contribution satisfies the area of the entanglement entropy. So it indicates that we can use tensor product state to represent the quantum state, higher dimensional quantum state very efficiently. And here I show you some example. First example is so-called polypod state proposed by Alexei Kitaev. So here the model is defined on the square lattice, but spin is in this representation, spin is located at the edge instead of the side. But then here we consider the four-body interaction like this, A and B. The A is product of sigma x, sigma x, sigma x, sigma x, and B is the product of sigma z. This. Then the point is that the ground state of this model is called the deep spin liquid state, non-magnetic state, and naively it is not so easy to represent this quantum state by classical computer. However, by using tensor product state, we can represent the ground state of this model by using only d equal to. Here is a concrete example of the non-zero element of our local tensor. And here we construct the square disk like this. And by using the only d to the d equal to, the ground state is exactly represented by this tensor product. So this is one example that the tensor product state can represent the non-trivial unit state. Another example is the ground state of the type model. Here, another type model on the honeycomb lattice. Here we consider the honeycomb lattice, and we have three different interactions depending on the direction of the bond. For example, horizontal bond we call that is D bond, and on D bond we have the interaction SGST, and on X bond we have the interaction SXSX or something. And it is known that again the ground state of this model is spin liquid, and the ground state is in the so-called the vortex free sector. That means that the flux operator defined as like this. Here, sigma is the Pauli matrices commute with our Hamiltonian, and also the different flux operator defined on different bucket commit each other. Then, so this WP gives us the conserved quantity. Anyway, then the ground state is in the sector of vortex free. It means that all eigenvalue of this flux operator is equal to 1. Anyway, the point is that the ground state is a spin liquid state, and the gap or gapless is determined by the parameter of this J. So if the interaction is anisotropic, highly anisotropic, we have the gap spin liquid state. But if the interactions are isotropic, nearly isotropic, we have gapless spin liquid state. Sorry, I didn't discuss it before. In this case, this spin liquid state is gap. So we have the finite gap in this state. But in this type model, type honeycomb model, or the isotropic region, the ground state is gapless. And here I show you our study. So by constructing some tensor product state like this, it is just a projector onto the vortex sector and applying to some ferromagnetic state, we construct some quantum state with bond dimension 2 represented by tensor product state. And the point is that this state is actually the critical Japanese, and the criticality is same with the type spin. By in addition, by applying the additional tensors to this tensor product state, we increase the accuracy of our tensor product state. For example, this table shows the bond dimension D and the corresponding energy error, relative energy error is. So in the D equal 2 state, we have the error about 20%. But if we construct the D equal 8 state, the error is about 0.007%. So very small. Okay. Anyway, this is the one example that the Japanese liquid state can be efficiently, accurately represented by the tensor product.
Surely, I have a question.
Okay.
So this is the result of the wide choice of the initial spin
That's
state.
right.
This is the result of the wide choice of the initial spin configuration, which was based on the Lucas state slide. So when you are starting from the random initial spin configuration, for example, so I think the tensor network will be suffered from the optimizing the
Okay.
state,
So-
I think.
Let me explain a little bit more about this construction. Here, we didn't perform the optimization by applying this. So what we consider is that this is answer, and this R operator have a variation of parameter, right? Single variation of parameter. And so in this case, this is just an answer, not the, for example, imaginary time definition or something.
Yeah, but this is the, I think, the initial spin configuration, right?
But what do you mean initial?
For example, in the variational Monte Carlo method, so we set up, I think, the first initial spin configuration.
Okay, so you consider this
Yeah.
as the initial.
Yeah.
Okay. Yeah, but okay. So we don't consider that such kind of setup. So this is to include the property of this Lucas state. So we cannot neglect this part. This part captures the important long-range quantum entanglement. So we cannot neglect or we cannot change this part. We only change this part. So, if we consider random state up here, this answer is not good. Yeah, so if we want to optimize our tensor network state, starting from by using, for example, imaginary time evolution, the initial state is very important. But here we don't consider such kind of optimization. But just so actually there is only the two variational parameter here. So this is the defined way in the standard tensor network simulation.
So how do you optimize it? How do you?
Yeah, this is the very, how to say, heuristic way. Just calculate the energy, and we perform the grid search. Oh, because we have only two parameters, so we can perform the grid search, and we find some good points.
But again, I keep it in whatever you started with, it all depends on it. It's just like a variation of Monte Carlo. It's some
Okay,
variant of it.
yeah. I will do that point later. But here, what I want to say is that this answer is very good, and we obtain this good answer or approximation. So our tensor product set can represent the Japanese quantum spin liquid state very accurately. One example. This is just one example. Technically, it is not so difficult because we know the good initial state in this case.
Yeah, and what is the full dimension of this? Like, this whole
Dimension.
dimension of the whole system?
Okay, this is the infinite size system.
Yeah, but the Hilbert space, what kind of dimension?
Hilbert space dimension. What do you mean the Hilbert space dimension? Like
Yeah.
the DMRG, I mean the DMRG.
That's right.
If for example this one, this value, so D is the dimension of the one leg in the tensor network.
It was such a great accuracy.
So this is because the distance of the state is very good.
Okay, so now the Rukuga state is just written by the D equal to tensor network.
Yes.
Right?
Yes.
So, and you would like to increase the D value. I see.
More accuracy of the energy expectation by
Yeah. Let's discuss later, sorry for interrupting.
Anyway, this is the not optimization in some sense. The purpose of this slide is I show the one result that some practical tensor network state can achieve the very good accuracy energy for the gapless spin liquid state.
And if it is a perfect diamond set, then yes.
Okay. Then this example indicates that we can use this tensor product state as a variation of a function. So in this step, we need to optimize our tensor as discussed in this question. However, if we consider infinitely large tensor product set, there are several difficulties coming from this infinitely large tensor. Now, first one is that the optimization of the infinitely repeated tensor is highly non-linear. So there is some mixture of the different part of the tensor, but we assume that the tensors are same. So the optimization is very difficult. This is the crucial difference between the finite size system with the different tensor. But here we repeat the same tensor. And also we need to introduce contraction the tensor network as we discussed. So it means that we have some numerical error in the energy. That is the cost function of the variation of optimization. So the optimization is very important, but I think I don't have enough time. So I quickly explain what is the important point in the optimization. Okay, basically to use this tensor product states for the variation of calculation, we use the two kinds of the optimization technique. The first one is imaginary time evolution, and the other one is variation optimization. The second one, this variation optimization, is look like the DMR. Like, and the first one is just like a power method. So we apply the exponential with okay. And yeah, there are several techniques, but the main numerical technique is unlike the EBD explained in the previous lecture yesterday. We introduced the Suzuki-Rota decomposition of this imaginary time evolution operator, and we solved the local problem like this, or global problem by considering the surrounding environment. And we want to approximate the tensor times tensor time imaginary time evolution operator to the just the tensor network. And here we introduce the approximation so that the bond dimension between the A and B does not increase. So to keep the calculation with constant computation cost. Anyway, we perform the imaginary time evolution to optimize our tensor network starting from the some initial state. And as we discussed before, this procedure, the initial state is very I will discuss. Okay. Anyway, the other method is the variation of calculation. So we just calculate the energy for a given quantum state. Then we change the parameter of the tensor network so that we reduce the energy. So in order to perform this calculation, we need to calculate the derivative of the energy with respect to the tensor element. And for the infinite size system, it has been very difficult. But from the 2016, some groups developed the technique to evaluate the derivative with respect to the tensors, and nowadays we can apply this variation optimization for the infinite size tensor product state. And I would say that you should use the variation optimization nowadays, but this imaginary implementation is very easy in the case of the imaginary time evolution. Okay, then I will skip the technical details. Okay, and so here I show you some results from my work. So by using the infinite tensor product state, for example, we can calculate the magnetization plus of the component that is higher than anti-ferromagnet, very good accuracy, or we can consider the square frustrated square this model. This model is relevant for some organic compound synthesized by this professor or something like that. Anyway, we can apply the tensor product state for the real calculation. Real calculation is beyond the text. And we can also apply this technique to calculate the phase diagram of the type materials. Materials means that previously I introduced the pure type model, so that it contains only the anisotropic interaction. But in the real materials, we have the very complicated interaction. We can evaluate such interactions from the DFT, for example. Then the actual model contains the type interaction, high-level interaction, and off-diagonal interaction, plus third level and second level interaction, or something like that. But we can apply the tensor product state to calculate the ground state phase diagram of this complicated model. And actually, we know this kind of phase diagram. So now we can apply the tensor product state method to investigate the problem closely related to the experiment. Okay. Then finally, I'd like to comment on the importance of the optimization technique. So as we discussed, the quantum state obtained by imaginary time evolution tend to be biased by the initial state. So as you said. So it means that in practice, it is not easy. Sorry, this is a mistake. It is not easy to obtain a quantum spin liquid state, even in the case of the type model. If we start from the random state and we apply the imaginary time evolution, and as I explained, as I showed you, the tensor product state itself can represent the gapless type spin liquid, but very efficiently, accurately, but it is very difficult to reach the such state if we start from the random state. And for the frustrated spin system, it is also difficult to obtain the bound state among several candidates of the augmented state with small negative analysis. Okay, so in these programs, we want to use a more sophisticated optimization technique, and that is basically the variation of technique. Right, with this one.
Here, one more comment I will make. So whenever you have the regionless any projection operator that imaginary time evolution is, I mean, we'll have a hard time distinguishing because the energetically these two the same.
Yes, yes, right. I think so. But another difficulty coming from the fact that we treat the infinite size system. So, and we only treat the energy density instead of the energy itself. And so it means that the finite gap, the two states which have the finite gap independent of the system size give us the same energy density. This calculation. So there are several difficulty coming from infinite size. Okay. Anyway, then I'd like to recommend you to use the variational method, and I will skip the technique, but this is the very important message. Maybe I will need to explain this one. So if we apply the infinite size tensor product state method to the stack model, and we try to approximate, optimize the such tensor product state by imaginary time evolution, the final state. So vertical axis is the energy density, and the horizontal axis is the imaginary time. And starting from the different random state, then the final state highly depending on the random initial state. And another problem is that this curve gives us the energy 4.193, but this is not the lowest energy for the given tensor network. However, if we use this variational optimization technique, then we smoothly obtain this kind of curve. And the point is that the flux that characterize the nature of the strength, then liquid becomes 1 directly, so that we obtain at least the non-magnetic state. And then this is the comparison of our energy to the here. Solid line is the exact one, and dotted line is the previous string gas state. So artificially designed our tensor network state. So by using the variational optimization, we obtain the better state than the artificially designed string gas state previously by using the variational. So it is very important to use the good optimization technique to perform the variational calculation using the infinite tensor product. Okay. I'd like to mention how to use the finite temperature calculation quickly, very quickly. So as I explained, so far we consider the pure state, but we can generalize this idea to simulate the finite temperature state by approximating the density matrix as the tensor network decomposition. So here we can consider two types of the approximation. The first one is, so here we for the simplicity I use the one-dimensional system. So the density matrix means that this upper half corresponds to the row and bottom half corresponds to the column, for example. And we represent the density matrix as a matrix product operator like this, or we use the so-called purification technique. So it means that we consider this tensor network to represent the density matrix. There are good point and the bad point for depending on this representation. So in this direct tensor product representation, this density matrix not necessarily a positive semi-definite, but the computation becomes very simpler. And this representation gives us the positive semi-definite density matrix. However, it's not so efficient in some cases. There is some proof, or there is some example. Anyway, we can represent our density matrix by the tensor network state, and we can apply this calculation to the finite particle property. And I'd like to show you some results to apply this technique to the type model. And this is the final result. Sorry, let me explain. So by using the quantum Monte Carlo technique, we can represent the specific heat of this type model have the two peaks. So we know this result. And we want to reproduce this quantum Monte Carlo result by using the tensor product state approach. Then actually, by calculating the specific heat, we can reproduce the two-peak structure if we increase the voltage D. And corresponding to the two-peak structure, we have the increase of the flux. And so it means that the low temperature state goes to the specific state. However, by comparing the quantitative property between the tensor network approximation and the quantum Monte Carlo, we realize that the quantitative peak, the second peak, lowest peak, is much smaller than the true value. So it means that the tensor product state can calculate the finite temperature property for moderate temperature, but low temperature state, there remains some difficulty. So we need to improve our method.
So what is the temperature at which it works? I mean, because at higher temperature it will work because you have a
Okay,
very
so, right.
formulation.
So here the T is in the scale of J.
Almost J.
J.
That's very large.
So the difficulty appears around the 0.01 or something.
With this you can get even for a smaller system if you do the high temperature will be reproduced.
Yeah, okay. So the point is that here we consider infinitized system, and if we consider the finite size system, I can say that we can reproduce the two big structure fraction. So for example, 10 by 10 is very difficult, but 8 by 8 or something like that.
But if you see, if you take the very small cluster, if you want to do the high temperature calculation, then high temperature will be matched even for smaller clusters.
Yeah,
That's what
nice.
is our
I agree with you. But yeah, here I should do some benchmark result, but we can improve the quality of this low temperature peak, and actually we can almost reproduce this property in the calculation, but we need a huge computation.
And for the quantum Monte Carlo, there's no sign problem here.
So
here
in
you have-
this case, there is no sign problem. So in this sense, this is the result. So this is the special case. But if we consider the additional interaction, the magnitude, we cannot apply to this.
This is for pure type.
Yes, it is for the pure type.
The Monte Carlo can be actually it's really not really quantum Monte Carlo in the user.
Yes.
You
So-
they do the Monte Carlo for the flux parts, I guess.
Yes.
So the
That's
free fermion programming.
So we introduce the iron fermion. Next, with the wide fermion pattern exactly because that is free fermion, and finally remaining the cluster degree without this one. So yeah, that's it. Then, this is different from the usual standard worldwide. Okay, anyway, so my message is this one. So this is probably sorry. So this is the summary of my lecture. So today I introduce you what is the tensor network, the composition of tensor network state. My message is that by correctly designing the tensor network structure, we cover the area of the entanglement entropy, and so we can treat the higher dimensional system very accurately. But in practice, we need to take care about how to construct our very large tensor network or how to optimize our network. And in principle, we can apply our technique to the finite temperature property. But so far, there is some difficulty to apply this technique to low temperature system. That's it. Thank you for your attention.
Thank you for nice lecture and also keeping time. So we can take some questions.
So towards the last part of your talk, you explained how to use your technique to obtain this finite temperature properties for the guitar model. So is it possible to use your model also if you, let's say, add some small Heisenberg perturbations or something?
Yes.
Because then the integrability is lost.
Yes, of course. So the point is that here we just approximate our density matrix by using the tensor network, like this, for example. Then the remaining computational technique is same with the previous pure state calculation, and it does not depend on the details of the calculation. Sorry. Yeah, it depends on the connectivity of this, but depends on the does not depend on the details of the two-sided function. So we can apply this technique for any kind of the extended care. And so as you mentioned, if the state is not the spin liquid state at the low temperature, then probably the accuracy increases. But in some sense, this benchmark is benchmark for the very difficult situation.
A question. So ITPO stands for what?
Sorry, ITPO is, sorry,
Well, I just wanted to know, maybe you explain, but which corresponds to ITPO?
okay.
One
ITPO is here. So we can consider two kinds of representation. The first one is directly represent our density matrix as the tensor product of data. Instead, we use the so-called purification, and the purified quantum state is represented by the tensor product.
ITPO reverse.
Yeah, the first one. And at least for the one-dimensional system, it is not that good. But ITPO is more efficient. And,
Other questions or other questions from online?
Thanks for the nice talk. When you optimize the tensor product state, you use like the imaginary kind of evolution.
so
Is
some
it-
example.
Is kind of making the system to the maximum entropy state, or
So
I think of it
basically,
like it.
the imaginary time evolution optimize the state to the lower entanglement state. So because we have the area of the entanglement entropy for the class. So that answer your question.
I will ask you later.
Okay.
Any other questions? Okay. If not, let's time to speak again. We convene for the perspective talk in about 30 minutes at 3:45 India time.